Hello, this video is about mole to gram and gram to mole conversions, as well as gram to number of atoms conversion type problems. And then we'll end with balancing chemical equations. So the first thing I want to do is looking at these problems on this slide. Let's do a couple of them just to show you how this works. For the first one, we'll look at number 1. It says calculate the number of atoms in 1.7 moles of boron. Okay, so when we take a reading problem, we want to carefully pull out the information that's given in it. And so they're asking for the number of atoms in 1.7 moles of boron. So we have to come up with a plan of action for this solving this problem. So we start with what's given, moles of boron, B for boron, and we're going to convert that to atoms of boron. All right, so we have to know, is there a relationship between moles and atoms? And yes, there is. We know that 1 mole is equal to Avogadro's number of substances. So if it's 1 mole of boron atoms, that means we have Avogadro's number, 6.022 times 10 to the 23rd atoms of boron. All right, we're going to use this equality to make a conversion factor to convert moles of boron to atoms of boron. So we're going to start with what's given. I'll put that up. Let's change the color of the ink so we get something that's more contrasty. So I've got 1.7 moles of boron. And so I'm going to have a multiplication sign and a quotient bar. And what I want in the denominator is moles of boron, because that's what I'm trying to get rid of. And so I go to my equality here, and that tells me I need to divide both sides of this equality by moles of boron. So whatever, you can see, I'll do it to both sides, and then we'll see what happens. This side cancels out with that. That becomes 1, unity. So all of this conversion factor here equals 1, which that makes sense because we're not changing the quantity of boron we have. All we're doing is changing the units from moles to atoms. So what I have in parentheses here, that's what's going to be our conversion factor. So we would write 6.022 times 10 to the 23rd atoms of boron in the numerator. All right, we know we set the problem up right because the moles of boron divide out, become 1, and then we just need to take 1.7. So on your calculator, you'll put in 1.7 times 6.022, and then you'll look for a key on the calculator that looks like this. EE if you have a Texas Instrument calculator, or EXP if you have a Casio or Sharp calculator. So we'll put in, again, the 6.022 and then hit the EE key, and then we'll put in 23 and we'll hit enter, and we will get an answer of 1.02 times 10 to the 24th atoms of boron. Now, that's a rough answer. That's not my final answer. The final answer should only have 2 significant figures in it because 1.7 only has 2 significant figures. So the 2 significant figures, I look at this number, the 1 and the 0. Look at the 2, it's less than 5. So I'm going to round down. My final answer would be 1.0 times 10 to the 24th atoms of boron. All right. All right, let's look at another problem. Let's look at number 4 here. All right. So here we're kind of doing the opposite. They tell us how many atoms of a gold we have, and we'd like to know how much does that weigh. Now it says mass, and you're like, well, what unit am I supposed to use? Microgram, kilogram, or gram? I would focus on using gram, and the reason why, that's the base unit for mass in the modified metric system. So my plan of action here is to go from atoms, which is a number of particles, atoms, and I can't go directly to mass, which is in grams, because I don't know the relationship between atoms of gold and grams of gold. But what I can do is I can group these atoms together in a groups called moles, and then once I get the moles, I know I can convert that to grams, because all I need to know is how much does 1 mole of gold weigh. So to do this problem, we're going to use the same equality that we did before. And let me erase this so we've got some place to write. We're going to say that 1 mole of aluminum, or no, this is gold. 1 mole of gold equals 6.022 times 10 to the 23rd atoms of aluminum. Gold. All right, so I'm going to use that equality to make a conversion factor. So what I'm going to do is, instead of saying 5 million here, I'm just going to say 5 times 10 to the 6. That's an easy way to do it. So I've got 5 times 10 to the 6 atoms of gold. And here I want to get rid of the atoms of gold, and I want to be left with moles of gold. 1 mole of gold, or how many? Yeah, 1 mole of gold here. So in 1 mole of gold, there is Avogadro's number, 6.022 times 10 to the 23rd. All right. All I've done is taken both sides of this equality and divided by Avogadro's number. I'll just say AV. I want to write that all out. All right, our next step is we want to get rid of the moles. So 1 mole of gold, how much does that weigh? Well, you have to look at the periodic table. Periodic table, when we look at the masses on the periodic table, for gold, we get 196.967. Now, 196.967, that is, if we were talking about 1 atom of gold, that would be in atomic mass units. But now we're talking about Avogadro's number, 6.022 times 10 to the 23rd atoms of gold. And the advantage of boosting the scale up, or enlarging the scale to that size, is that a mole of gold weighs 197 grams to 3 significant figures. So again, what we've done here is, on the periodic table, it says gold weighs 196.967. We don't need all of those significant figures, because the measurement was only made to the ones place in 5 million. So 3 significant figures should be good enough. So if we look on the periodic table and we round 196.967 to 3 significant figures would be 197. And since we're talking about a mole of gold instead of a individual atom of gold, that changes the unit from atomic mass units to grams. So on your calculator, you would take, let's go back. On your calculator, you would take 5 exponential 6. You would divide that by 6.022 exponential 23. So this is going to convert the number of atoms into moles of gold atoms. And then we're going to multiply by 197 grams, and that's going to convert the moles of gold atoms to actual mass in grams. So when we do that, we get 1.6 times 10 to the negative 15th. But again, our final answer, because 1.6, we should only have one significant figure, my final answer would be 2 times 10 to the negative 15 grams. That's of gold. All right. So always say what it's of. Don't just say grams, because we need to know what it is. So does that sound reasonable? Yeah, it sounds reasonable because a mole of gold is 6.022 times 10 to the 23rd, and we only have 5 times 10 to the 6th. So we definitely have a much smaller quantity than what's in a mole. All right, let's move on. Next slide, this is pretty much just showing how we go from grams to moles to particles. And those particles can be atoms, molecules, or formula units. And again, to go from grams to moles, we need the molar mass of the substance. And then to go from moles to actual particles, we need Avogadro's number. And then if we're doing it in reverse like we did with gold, we went from particles, number of gold atoms. We used Avogadro's number to convert that to moles. And then we, once we got to moles, we used the molar mass to convert from moles to grams. So this is a good slide to look at to understand the process. All right, so this slide we're talking about chemical formula, formula weight, and molar mass. These are important terms, and we need to know what the differences are. So chemical formula is just a combination of symbols that of various elements to make up the compound. So again, a chemical formula, we've seen these all along, like H2O, that's a chemical formula. All right. Sodium chloride, that would be a chemical formula. The formula unit is the smallest collection of atoms that provide two important pieces of information. They identify the atom or ions and the relative number of each type of atom or ion. So a formula unit is still like sodium chloride. That is the smallest unit of sodium chloride, even though if we look at a crystal of salt, even one under the microscope, there would be billions of these sodium chloride units. So formula unit, we're talking about an individual unit. Maybe it's in a large structure, but it's an individual unit that keeps repeating itself over and over throughout the substance. Maybe we'll see a nice diagram of that. All right, so here's some chemical formulas, and you do need to be able to interpret these. So the first one is hydrogen. It's diatomic, which means two atoms bonded together. We wouldn't call this a compound. We would call it a molecule. A compound, remember, means two or more different atoms bonded together. This is two of the same atom. We'd actually call this an element. And if you've been following along with my other videos, here's a little mnemonic, a memory device to help you remember which elements naturally occur as diatomic substances on the periodic table. And that's Honcliffe-Burr, H-O-N-C-L-I-F and B-R. So hydrogen, oxygen, nitrogen, chlorine, iodine, fluorine, and bromine all naturally occur in nature as diatomic substances. So that's what's happening here. We have diatomic hydrogen. It's two hydrogens bonded together covalently. And that's what the subscript 2 represents, two hydrogens bonded together. And this, again, this is, we would call this just an element. We wouldn't call it a compound. And we could also call it a molecule, though. All right, for water, we have two hydrogens bonded to the oxygen. Actually, we've already seen this when we did the Lewis structure. We had something like this for the Lewis structure. All right. So that's saying it's 2 parts hydrogen to 1 part oxygen, or 2 atoms of hydrogen to 1 part oxygen. And that those 2 hydrogens are bonded to the oxygen. And the reason why we know that is hydrogen can never be the central atom. We also know that oxygen being in group 16 has 6 valence electrons. And so there are 2 bonding sites on the oxygen, and that's where those hydrogen electrons fit in so that oxygen feels like it has a full outer shell of 8. And we talked about that when we talked about Lewis structures. All right, sodium chloride, a little different. It is an ionic compound. And so what's really present in that sodium chloride is a sodium ion and a chloride ion. And the thing about ionic compounds, these are formula units. This is a chemical formula, but it would also be the formula unit. It is the simplest whole number ratio of one ion to another. All right. Same thing with calcium hydroxide. That's an ionic compound. The only difference between sodium chloride and calcium hydroxide is the hydroxide ion is a polyatomic ion. So it's all intact, this OH, and we've seen that in a table. The hydroxide ion is OH negative, and we know calcium being in group 2 forms a 2 positive ion. So that's why we have to have 2 hydroxide ions bonded to the calcium. And so, again, the hydroxide ion is called a polyatomic ion. And if we have more than one of those polyatomic ions, we must put the polyatomic ion in parentheses and then put the subscript outside the parentheses to say this is how many of those polyatomic ions are attached to the, in this case, the calcium ion. All right, on this slide, it says consider the following formulas, and they've actually got a typo in this first slide. The ammonium, they say we need 3 ammonium ions per sulfate ion. Now, there's a mistake. Is what you have to recognize here is that sulfate is a polyatomic ion, and it has a -2 charge. And the ammonium ion is a polyatomic ion, and it has a +1 charge. So what do 2 and 1 both go into? Well, they go into the number 2. So this 3 here should be a 2, not a 3. So you have 2 positive ammonium ions, and you combine that with the 1 polyatomic sulfate ion that has a -2 charge. So there's a typo. It should be 2 ammonium ions. And again, we have 2 ammonium ions, so we put parentheses around the ammonium ion, and we put the subscript outside the parentheses to say we need 2 of them. So when we break this down, though, in total, you would have 2 times 1, 2 nitrogen atoms in this compound. You would have 2 times 4, 8 oxygen. You'd have 1 sulfur, and you would have another... I said 8 hydrogen, not 8 oxygen. And then and we would have a total of 4 oxygen. All right. So you need to be able to look at a chemical formula and break it down into its individual elements. This next one is a special type of compound. It's called copper 2-sulfate pentahydrate. First of all, you may be going, why is it copper 2-sulfate? Well, remember, copper is polyvalent. That means it can come in more than one charge form, and most of your transition metals do. Copper comes in a 1 positive form and a 2 positive form. And so which form do we have here? Well, we know the sulfate ion just by looking at the previous example is a -2 ion. So since we only have 1 copper here, that means that copper has to be 2 positive. So knowing that it's copper 2 positive, we would write this as copper Roman numeral 2 sulfate. And sulfate, again, the name of the polyatomic ion. And then there are 5 waters attached. Now these waters are attached to the crystal of copper sulfate. And so we got 5 waters, so we say penta, that's the prefix for 5. And then we say hydrate, that means it's water attached. So copper 2-sulfate pentahydrate. These waters are weakly attached. If we heat this copper 2-sulfate above 100 degrees for a period of time, the waters will escape as a gas, and we'll be left with just copper 2-sulfate. Once we have only copper 2-sulfate, no waters attached, we would call that anhydrous. Anhydrous means without water, so anhydrous copper 2-sulfate. All right. So we could break this down. There's 1 copper atom in this compound, 1 sulfur, 4 oxygen, and then we would say 5 times 2, 10 hydrogen, and 5 times 1, another 5 oxygen. And here's a picture of what happens. Copper 2-sulfate pentahydrate's a nice blue crystal. It doesn't stick together much, so it can easily be spread. And then once we heat it up, notice the blue color goes away and we get a white powder, and that's anhydrous copper sulfate. Copper sulfate's used to kill algae in ponds. The downside of it is it also kills fish and definitely invertebrates like your snails and things like that. So some people put it in their ponds and their or lakes to kill algae. It's like I said, it's toxic to invertebrates. Here's a question though: if they both cost the same amount of money, which one would you buy, the anhydrous or the hydrate? Well, I'd buy the anhydrous if they were both the same amount of money, because the hydrate, you're paying for water. You're paying for water in that compound. Now, if it's just the same amount, yes, I would agree with that. If you do not plan to use all the copper sulfate immediately, maybe you would like the hydrated version. It doesn't seem to clump together as much or stick together as much as the anhydrous. The anhydrous will start pulling water out of the moisture out of the atmosphere, and it starts kind of clumping and hardening up into these big chunks. All right, when we hear the word formula weight, this is kind of an old term, but it does mean something to us. Formula weight means that we're talking about the amount of mass in an individual atom or molecule. And so when we're talking about formula weight, the key is, as you know, those units should be atomic mass units. All right? So formula weight of H2O, you would say 18.02 atomic mass units. And you say, how'd you get that? Well, you go to the periodic table, and oxygen weighs 16.00 atomic mass units. Hydrogen weighs 1.008 atomic mass units, but you got two of them in water. So 2 times 1.008 plus 16 gives me 18.02 atomic mass units. The key here, though, the key is when we're asking for formula weight, the units for mass are atomic mass units. All right? Now, another type of mass that we will ask for is called molar mass, and that's how much does 1 mole of substance weigh. All right, so if they ask us for what is the molar mass of water, you notice the number is still the same, 18.02, but the units become grams per mole. And that's really important, because remember, when we're asking for molar mass, we're not talking about individual atoms or molecules or compounds in this case. We're talking about Avogadro's number, and that's why it's grams per mole, and a mole is Avogadro's number of particles. So that's the beauty of it is that when we change the magnitude of how much we're dealing with, how much water in this case we're dealing with, we go from atomic mass units to grams. And that's important because grams is something we can weigh out on a balance in the lab. It's very difficult to weigh an individual atom or molecule. All right, so formula unit. This is what we were talking about previously. A formula unit is the smallest collection of atoms from which a formula of a compound can be established. So let's do the one on the right here, the methane. Notice the covalent compounds. The formula units are just individual molecules of methane, and they act independently in terms if they were a gas. And so they're individual molecules of methane. Now look at the salt. When you look at salt, it's actually an array of chloride ions and sodium ions, and it's kind of hard to tell. Like if I'm looking at this chlorine here, is it attached to that sodium or this sodium or this sodium? You know, there's different ones that are touching it, and so that's the question. Which one of these sodiums goes with which chloride? So this is a big array of sodium ions and chloride ions. But the repeating unit within this whole crystal is NaCl. And that makes sense because sodium's a positive one ion and chloride's a negative one ion. And if this full crystal, this full block or cube, is to be neutral, you got to have the same number of positive sodium ions as you do the negative chloride ions. So that's what we mean by formula unit. We're picking out the smallest repeating components of that substance. All right. So the example of this calculation down here, they're asking you for the molar mass. It's funny, they show you how to calculate the formula weight first. That's what this is. And so when we multiply this all out, we would have gotten 149.10 atomic mass units. But because they're asking for molar mass, we know that means for a molar quantity. And so the units change from atomic mass units to grams. So 149.10 grams per mole would be the molar mass of ammonium phosphate. And this one's done correctly. Phosphate's a -3 ion. Ammonium's a +1. That's why you got to have 3 ammonium ions for every one phosphate. All right. So molar mass, we're talking about Avogadro's quantity of material. The numbers that we get to calculate that are on the periodic table, just like the numbers we get for the atomic mass or formula weight. What's neat about it is the numbers are the same, but again, when we're talking AMUs or atomic mass units, we're talking about individual molecules or atoms. And when we're talking about molar mass, we're talking about Avogadro's quantities. All right, so when we go to the periodic table and we want to look up how much 1 mole of carbon weighs, we look on the periodic table into 4 significant figures carbon weighs. 1 mole of carbon weighs 12.01. Now, just a refresher here. Remember how that 12.01 came about. We go out and scoop up some pure carbon. We run it through a machine, and it determines the percent occurrence of each isotope of carbon. Now, I think there was 3 isotopes of carbon, carbon 12, 13, 14. And so when we average those, remember it's called a weighted average, we get a mass of 12.01, and that's what we see on the periodic table. So that average mass, if we're talking about an individual carbon, we'd say 12.01 atomic mass units. But since we're talking about a group, a mole, 6.022 times 10 to the 23rd carbon atoms, we would say 12.01 grams per mole. All right. So a mole of any element has Avogadro's number in it. All right, so the next concept is writing and balancing chemical equations. And a chemical equation is just a shorthand notation using chemical formulas to write a chemical reaction where on the left-hand side we would have the reactants, then we have an arrow which we call the chemical yield sign, and then we have on the right-hand side of the arrow the products. So reactants on the left-hand side, products on the right-hand side. So you need to identify the products and reactants. Again, reactants on left of the arrow, products on the right. A lot of times you should identify the physical states of the matter. Like, is it a solid, liquid, gas, or aqueous, which means dissolved in water. Solid, liquid, gas, or aqueous. And that should be in parentheses. All right. And you say, well, how do I know if the substance is a solid, liquid, or gas? Well, if you're doing a reaction at room temperature, if you'll look on the periodic table, most periodic tables, your standard periodic table, shows that some elements are coated with black. They're in black symbols. Black represents solid at room temperature. Some symbols, especially group 18 and some of the nonmetals, is coated in red. And if it's coated in red, that means it's a gas at room temperature. And then still yet, there are 2 elements on the periodic table at room temperature. We consider them liquids, and that would be mercury, Hg is the symbol for it, and bromine, Br is the symbol for it. So there's only 2 on the periodic table that are considered liquids at room temperature. Another thing you may see is this delta symbol. That means energy, and so it could be heat. Generally, that's what it indicates. But if you see a delta symbol, it says we're applying energy to the system. And then the last thing, the equation has to be balanced. And the reason why is because back in Chapter 1, when we talked about Dalton's atomic theory that starts the whole foundation of chemistry, matter cannot be created or destroyed, so all matter has to be accounted for. So we can't have more matter than we end up with, otherwise we'd have serious problems. And we can't have less matter than we end up with, because again, we would have serious problems that everything would go away eventually. All right, so what we have here is our first example of a chemical equation. And so you notice the reactant, what's the name of this reactant? Be careful. Mercury is a polyvalent metal. So this is, we know oxygen is 2 negative. We know hydrogen is 2, or the mercury has to be 2 positive then. So this is mercury 2 oxide. And that's going to, we're going to heat that up. And the products are going to be mercury liquid and oxygen gas. All right. So this is a red solid. It's funny, we used to do this lab when I was in high school to generate oxygen. But can you imagine we're heating something up that releases mercury liquid, which then we could be breathing that. So I don't think they should generate oxygen anymore like that. But I just can't believe we did that a lot when I was in high school. And now they're, if you spill mercury on the floor, you have to evacuate the room. And then you have to use special equipment to get it cleaned up. So here what we look at is, like we look at this oxygen. I always look at something like this, and I notice there's 2 of them here. Well, there's only 1 oxygen here. So that's why we have to put this 2 in front of the mercury oxide. That's called a coefficient. So that what that says is I have 2 mercury 2 oxides now, and that's going to break apart and form 2, well, let's do it this way, 2 mercuries. And the oxygens are going to join together and form oxygen like that. So that's the way we think of this equation. You can think of it in terms of individual atoms and molecules, or you can think about it in terms of moles. But it's always kind of neat to think, or I think more helpful to think of it in terms of individual atoms initially. So this would be like 2 molecules or formula units of mercury 2 oxide. When heat is applied, will form 2 atoms of mercury in a liquid phase and 1 molecule of oxygen. All right. Products must be specified. Again, matter cannot be created or destroyed, so you've got to have the same number of each atom on both sides of the chemical yield sign. And also don't forget your phases there. Again, this is a new one probably for you, that delta means energy is needed. Yeah, mercury 2 oxide doesn't spontaneously change into mercury and oxygen. You have to add energy. And again, physical states are important. Again, if I were looking at this, I'd look at the periodic table, and it says mercury is a liquid at room temperature and oxygen is a gas. And so this one would be a little harder, but a lot of compounds are solids at room temperature. So matter is not created or destroyed in a chemical reaction. And so all matter has to be accounted for. And remember, in a chemical reaction, you are not changing from one element to another. And that's kind of what, the first thoughts of alchemy were. We're going to try to change lead into gold, or a cheap metal into gold. That can only be done by changing the protons in the nucleus. So all we're doing here is rearranging elements to make different compounds or different molecules. So what's the biggest indicators that a chemical reaction has occurred? To me, the number one is the one on the bottom here, color change. When you pour bleach on your blue jeans and they turn white, that's a chemical change. That indicates a reaction has occurred. When you toast a piece of bread and it turns brown, that's a chemical change. Or when you burn a piece of bread and it turns black, that's a chemical change. Or when you, maybe if you've cooked some red cabbage and you add a little bit of something acidic and you see the red cabbage juice change colors, that's a chemical change. All right. Other things, yeah, a lot of times when you see a release of gas, it could be a chemical change, like when you add vinegar to baking soda. But sometimes it's not. Sometimes the gas is trapped in something, and all you're doing is dissolving the salt away from the gas or something like that. Like, I don't know, if you remember Poppin' Rocks candy, there's no chemical change there. It's just releasing the carbon dioxide trapped in the candy. So you have to be careful with release of gas. Formation of a solid, if you're adding two chemicals together and all of a sudden a solid precipitates out, that's probably a good indication that you've had a chemical change. Now, if you just keep adding salt to water and it starts sinking to the bottom, that's not a chemical change. So these are a little tricky. That's why I think this color change should have been number one. And same thing with heat produced. If you add two chemicals together and it gives off heat, that may indicate a chemical change. Other things that can be subtle is heat or light's absorbed or emitted. Although again, something like crunching up a breath mint and it sparks, that's a physical process. It's kind of like quartz. When you compress quartz, sometimes it'll spark or give off light. So these are even more subtle, and I think they'd be hard to defend unless you know the exact reaction. All right. So there are really four types of chemical reactions. There's four patterns of chemical reactions. There's a combination reaction. That means we're going to be taking like A plus B and it forms AB. Decomposition, just the opposite. You start off with something like AB and it breaks apart into component A and component B. Single replacement, where like maybe a copper substitutes a silver, which we're going to see that. And then double replacement is probably the hardest one. It's where both components of a reactant swap with the other two components of another reactant. So we're going to see examples of this. So this is what combination looks like. A, B forms AB. A, B forms AB. So you'll generally see two things on the reactant side and only one substance on the product side. That's why it's a combination. Next slide is decomposition. Oops, what happened? Did I miss one? So decomposition, you start off with one substance and you end up with more than one substance. So here we started off with that mercury 2 oxide, and it decomposed after applying heat into mercury and oxygen gas. Or calcium carbonate. This is a common material in Lexington, Kentucky. There's a lot of limestone under Lexington, Kentucky, and it's being quarried or mined. And they take the limestone and they heat it up, and it changes into calcium oxide, also called quicklime, and carbon dioxide is released. And the quicklime is used to either minimize dust in like coal mines, and it's also used as a soil softener. Some people say sweetening the soil, so that's what it's used for. Then you have the single replacement. So what you see here is A knocks out B, and then B comes out here. So B becomes by itself, and A substitutes for B. So single replacement is not too hard to see. You generally have an element, and then you have a compound, and you see the element knock out one of the elements of the compound, and then we get the element that was in the compounds out by itself. So this would be a way maybe of purifying gold or silver in this case. So you want to, silver maybe is attached to the nitrate, but you don't want the nitrate. You want pure silver metal to maybe make jewelry or something. This would be one of the ways you would purify it. Same thing here. The sodium knocks out a hydrogen here, and we get sodium hydroxide, and then hydrogen gas is given off. And then the last example is a double replacement where A, B, C, D. So you got to have something that's got multi-components within the compound. A attaches to D and B attaches to C. So we get AdCb. So this is called double replacement. Two substances completely change their partners. So a lot of times where you see double replacements, maybe an acid-base reaction like this one, hydrochloric acid reacts with sodium hydroxide, the NaCl stick together and the H and the OH stick together, and that forms water. So this is going to be a really important reaction coming up in our acids and bases chapter. So we call this the neutralization of an acid, or neutralization equation, where we have properties of an acid in HCl and properties of a base in sodium hydroxide. But once these react, we end up with salt and water. Right? Precipitation reaction. The lead is attached to the chlorine. It actually forms a solid according to the solubility rules. And then the sodium is attracted to the nitrate, and we form another compound here. But it's water soluble. That's why it's aqueous. But what this looks like is you have two clear, colorless solutions. One of lead nitrate in water, and one of sodium or lead 2 nitrate, I should say. Lead 2 nitrate in water. Again, it's polyvalent, so that's why we call it lead 2 nitrate. Nitrate's a -1 ion, and lead's a 2 positive ion. And so this is lead 2 nitrate in water in one test tube. And in the other test tube, we have sodium chloride. When we pour those together into a beaker, all of a sudden, the solution looks like milk. It's milky white. And that's because this solid was formed, and it looks like a white precipitate in the beaker. So you go from clear, colorless solutions to a white, milky-looking solution, and that's a double replacement. All right. So when you write a chemical equation, first of all, you got to read. A lot of times you do this. You say hydrogen reacts with oxygen. Well, you got to know the Honcliffe bird, that hydrogen naturally occurs as a diatomic gas, and oxygen naturally occurs as a diatomic gas. And so when these combine, they form water. That says that produces water. But you notice already there's 2 oxygen on the reactant side. There's only 1 oxygen on the product side. So we're going to have to put a coefficient of 2 in front of the water. So that gives me 2 oxygen, but now that gives me 2 times 2, 4 hydrogen, so I have to put a 2 in front of the hydrogen. So that's the way we would balance that. And your book talks about, again, mass has to be conserved. We've already talked about that. Here is a general technique used to balance equations, break it down into each individual element. I generally don't do that. I think it takes too much time, but if you're lost, it is something to try. All right, here's something I see students do. They would say H2 plus O2 equals H2O2. See, it makes it nice and easy. There's 2 here and 2 here, 2 hydrogen, 2 oxygen. But H2O2 is not water. Water is H2O. H2O2 is hydrogen peroxide. Totally different substance, totally different chemical properties. So once you establish what your reactants and products are, the only thing you can do is change the numbers out in front of the atoms and molecules. And so that's the key, is that you can't change the subscripts, because if you change the subscripts, you'd be changing the substance altogether. All right, we've pretty much done this one. Let's move on. Let's move on. All right, so this is a kind of a confusing slide too. What they're talking about, if you've read the book, it's nitrogen combines with hydrogen to form ammonia. That's the underlying theme. Well, what's wrong with this first equation is we're not forming ammonia. We're forming hydrazine, which is jet fuel or rocket fuel. So we're not forming ammonia. So that's why this one's incorrect. Incorrect equation. Because we're not forming the right product here. All right. In the second equation, what's not right is nitrogen occurs as a diatomic substance, not an individual monoatomic atom. And hydrogen doesn't occur as a triplet. It occurs as diatomic atoms, like so. So they do have the correct product, ammonia, NH3, but they don't have the correct reactant. So here's what it should be. Diatomic nitrogen, one of those, reacts with 3 molecules of hydrogen. And so this nitrogen is going to attach to, or 3 hydrogens are going to attach to this nitrogen, and then the other 3 hydrogens are going to attach to the other nitrogen, and we get 2 ammonias. So this one is correct. 1 mole of nitrogen, 3 moles of hydrogen yield 2 moles of ammonia. So I'd look over this slide. I think it shows you conceptually what's going on with the balanced chemical equation. All right, so here's some equations to balance, and this will be my last slide here. To me, the best way to balance these things is to look at the most complex substances. Like this substance, acetylene, has both carbon and hydrogen in it, and notice it's in one compound and then it's in another compound here. So I would focus on the acetylene to balance. So I see a 2 carbon here, so I'd put a 2 in front of that. Carbon dioxide, that gives me 2 carbon. And I already have 2 hydrogen on both sides. So the only thing it's not balanced is the oxygen. So on the reactant side right now I have 2 oxygen. On the product side I have 2 times 2, which is 4, plus 1. I've got 5 oxygen. So I've got an odd number of oxygen on the product side and an even number on the reactant side. So when I have an odd-even combo, the quick way is just to say 5 halves here. Take the 5 and divide it by the 2. And what that would do for me is it would give me the right number of carbon, the right number of hydrogen, and then this 2 and this 2 divide out, so that'd give me 5 oxygen, and I'd have 5 oxygen on the product side. Now, some people don't like a fractional coefficient, in fact, but it is legal. So if you want to get rid of the fraction, you just multiply the entire equation by 2. So when you do that, you would get 2C2H2 plus 5O2 yields 4CO2 plus 2H2O. And you can count that and make sure everything adds up. All right, next equation, we have a double replacement reaction. So I would focus on this. I think it's the most important. And so iron 3 nitrate. Iron 3 nitrate. And so notice there's 3 nitrates. Now what's neat about this nitrate, this polyatomic ion remains intact. So I'd balance this as a whole. So I put a 3 out in front of this. That'd give me 3 nitrates. And I would then look at the iron, and we see that we got the same number of iron on both sides. So I wouldn't worry about that. And so we would look at this and say, oh, well, I've got 3 chlorines here, so I'm going to have to put a 3 in front of that. And that balances the equation. This 3 gives me 3 silver. This 3 gives me 3 silver, 3 chlorine, 3 chlorine. All right. Next one, I'd look at this substance. I'd put a 2 here and a 3 here. That would give me 6 hydrogen and 2 carbon. And then I'd add up my oxygen, 2 oxygen on the reactant side, and a total of 4. 2 times 2 is 4, plus 3, 7 oxygen on this side. So I'd say 7 halves. Or I could multiply again by 2, and I'd get 2 C2H6 plus 7 O2 yields 4 CO2 plus 6 H2O. All right. And then the last one, I would look at this substance. I know I need a 2 here to make this 2 work here, and I need a 3 here to make 6 hydrogen on both sides. So that's the way I would balance that. All right. I hope this has been helpful. We will continue on with Chapter 4, getting into stoichiometry problems in our next lesson. Thank you.